Radiofrequency instrumentation is expensive, but we can detect a high-frequency signal with a simple multimeter and a small device called Schottky diode. We will devote 3 videos to Schottky detectors, and this is the first one. This figure shows a simplified structure of a Schottky diode. This device is essentially a metal semiconductor junction. It is very similar to a p-n junction, where the top conductor plays the role of the p side. The behavior of a metal semiconductor junction is strongly dependent on the doping concentration we use. When the semiconductor is lightly doped, the resulting junction is rectifying. This means that it behaves like a diode. But if the doping concentration is high enough, the space charge layer becomes very narrow and carriers can pass through it equally well, either from the conductor to the semiconductor or the opposite way. Therefore, in this case, we just have an ohmic contact. The Schottky diode offers two key advantages when working as a detector. The first one is that it can provide currents with very low voltages as compared to a p-n junction. This means very high sensitivity. The second advantage is that it has a very fast time response. A silicon Schottky diode can work to frequencies as high as 40 GHz if the capacitance is made small enough, and this can be done by reducing the anode area. And today, gallium arsenide and indium gallium arsenide Schottky diodes are among the best options to detect signals from less than 100 GHz to terahertz frequencies. This is a simplified structure of a typical detector based on Schottky diodes. The diode is connected in series and the output stage has a parallel capacitor that behaves as a low-pass filter. With this configuration, the diode is able to provide a DC voltage that increases with the input power. The IV curve of a Schottky diode can be predicted by the Shockley model, which gives this expression for the current. I0 is the reverse bias saturation current, V is the voltage across the diode, and N is called the ideality factor and indicates how close the diode is to an ideal one. A high-quality device should have an ideality factor close to 1. Typical values are between 1 and 1.1. The Boltzmann constant times temperature divided by electron charge is usually called thermal voltage and is represented by Vt. Here we will use this label Vt to represent the product of the thermal voltage and the ideality factor. Doing so, we will simplify the equations quite a bit. V is the difference between the input voltage, which we call V sub Rf, and the output voltage, called Vout. Once we get Vout as a function of the input voltage amplitude, we will immediately obtain its dependence on the input power. This IV equation is clearly nonlinear, and this is essential for our purposes. After all, we need to do a frequency conversion. Our goal here will be to obtain an equation to estimate the output DC voltage from a given amount of input RF power. We will consider first a general case in which our device is represented by a nonlinear IV curve. If we assume that our signal is weak enough, we can estimate the current from the first terms of the Taylor series expansion. In order to avoid strong errors, the total voltage in terminals of the device must be low in comparison to the voltage change we need to apply in order to observe a significant change in the current. The first term will always be 0, since we are doing a Taylor series expansion around 0. If the voltage at the device terminals is 0, the device is in equilibrium and no net carrier flow can exist. Furthermore, we can give labels to the derivatives in order to get compact equations. Here we identify the device conductance with the standard letter G, and its derivative will be G'. Let us take the first two terms of the Taylor series. The total voltage difference at the terminals of our diode is Vrf minus Vout, and both voltages depend on time. But there is an important difference between them. Vrf represents the input signal given by an external generator, and it is a pure sinusoid. However, Vout is the response of the device to the input signal, and since the device is not linear, it cannot be a pure sinusoid. It must contain harmonics. This seems terribly complicated, but now we have a valuable help from the capacitor we connected at the detector output. It is working as a filter. Therefore, among all the harmonics the device has generated, only one will survive, the DC component. But the DC component of a signal is just its average value. In other words, Vout can be assumed to be constant. Therefore, in the forthcoming equations, we will remove the time dependency of Vout. We need to convert the current we have calculated into the voltage we will measure. To do so, we must take into account the input resistance of the instrument we use for the measurement. Might be an oscilloscope, but a multimeter will always offer better sensitivity. Anyway, let us call this resistance RL, since it is actually a load resistance. The output voltage we are looking for will be this resistance times the average current. And the current is the sum of two terms. Let us calculate them separately. We know that Vout is constant and VRF is a pure cosine function with an average of 0. So this average operation will reduce the first term to minus Vout. The second term is the square of a difference, but the product of VRF and Vout has again no DC component. Therefore, only the square of VRF and the square of Vout remain when doing an average. But remember that VRF is a cosine function. With some trigonometry, we see that the average of a squared cosine is just 1 over 2. Now we gather all terms and obtain a beautiful and compact equation that relates Vout with the voltage amplitude of the input signal. Okay, now we can move all the terms depending on Vout to the left, and this allows us to present the first important conclusion of all these. We can see that the term depending on VRF is proportional to G', but G' is the derivative of the conductance. Let us assume that our device is linear. If it is linear, G is constant and G' is 0. As a result, we can apply to the input a radio frequency signal as large as we want. We will detect nothing. In other words, we need a nonlinear device as we anticipated. Okay, now it is time to apply all this to a Schottky diode. For this particular case, the derivatives are easy to calculate. Let us substitute these factors in the general equation, and we see that there is a dependency on the product of the reverse saturation current of the diode I0 and the load resistance, but we can still simplify more. Let us gather I0 and RL into a single constant which we call K. And now let us focus our attention on the term that goes with Vout squared. This term makes the dependency between Vout and V0 a bit complex, but in practice it is not very helpful in this model. And the reason is that we have already assumed a small signal regime, which formally implies that the output voltage is negligible in comparison to Vt. So if this is the case, we see that this term is much less than this one. And if it is not the case, we should add higher order terms of the series expansion that we have already ignored. So we can safely remove it from our equation. Now we convert the input voltage into the input power we use to measure in practice, where set in is 50 ohm. We got the equation we were looking for. We can extract from this equation a couple of remarkable conclusions. The first one is that our device provides in a small signal regime an output voltage that is proportional to the input power. It is for this reason that we say that our device is a square law detector. And the second one is that a perfect detector provides an output signal that is not dependent on the input frequency. However, we will see that in practice our real-world detectors are not perfect. We can have losses at the filter stage that might need to include additional resistors in our model. For instance, if the parallel capacitance is lossy, we would be forced to add a parallel resistor. We also have deviations from the perfect square law due to the series resistance of the diode. This resistance produces a voltage drop that depends on the current. Therefore, one needs to solve the diode equation for the current with a voltage term in the exponential that depends on the own current. This means a self-consistent approach. And of course, we also would need to access the diode of the detector in order to measure its series resistance, and this is not always possible. Finally, we will have mismatches between the generator and the detector, which might lead to changes in the sensitivity with respect to the frequency, and also to an overestimation of the voltage to be measured. We certainly need to do measurements on real-world devices to check all this. This will be the subject of our next video.